Mr. Palladino, and welcome to chemistry. We're going to talk today about the scope of chemistry and what is going to be the background of everything we do this year. So here's a picture of a fugu, or a puffer fish, which is a sushi delicacy. However, it can be lethal if the chef does not remove a special gland that contains a toxin that is paralyzing. However, this toxin has been isolated and used for good in helping cancer patients. So this is but one use of chemistry or a chemical. So why is it so vast? Because everything around us is made out of matter. So matter is anything that has mass and occupies space. Space would be volume. So things that have mass and volume are considered matter, and that's almost everything around us. The other thing that we talk about oftentimes is energy. And Einstein has created a neat little thing called E equals mc squared, which we'll talk much later in the course, which is a formula that relates energy, E, to mass, which is a direct proportion. Okay, and this c is the speed of light, which is a huge number that's squared. So the things that change the two apart is an amount of energy that's really, really high. So a small amount of matter or small amount of mass contains a lot of energy. That's why we have things like nuclear energy. So if we look in this picture, we see trees, we see buildings, we see water. These are all examples of matter. So what does chemistry do? Chemistry we can define as the study of the composition, so key word there is composition, of matter and the changes that matter undergoes. Okay? So composition is how it's put together, its structure, and the changes it undergoes. And it affects all of us all the time because all living and non-living matter, living things are made out of matter. Okay, here's a question. If I have an advertisement and it says that the juice that I want to drink is all natural and free of chemicals, what's wrong with that statement? I'm going to have you give you some possibilities, write down your thoughts and play pause it. So I'll catch you in a minute. Did you say everything's made up of matter? So everything contains chemicals, even all natural products? Everything is a chemical. Don't think of chemical as bad things. It's everything around you. Next, we want to break chemistry down into 5 traditional areas and talk a little bit about each of these areas. There are 5 areas: organic chemistry, inorganic chemistry, biochemistry, analytical chemistry, and physical chemistry. We break chemistry down into these 5 major areas. And when you get into university, you might even break them down even further. Okay? So these are our 5 areas of chemistry. So what are each of these areas? Organic chemistry deals with any compound that contains carbon. Oops. Okay, now carbon is this element, C. Okay, and there's many, many things that contain carbon. Now you might wonder, why did we call it organic? Well, originally it was thought that all carbon-containing compounds came from living matter. So that was organic. We found today that that's not quite the case, so we've summarized it as saying anything that contains carbon. Okay, so what would an organic chemist work on? Organic chemist might work on plastics, okay? Organic chemists might work on pharmaceuticals. The next area is inorganic. Since the prefix in means not, it just means that it's not organic chemistry, and that means it's basically things that do not contain carbon. So it's everything else on the periodic table except carbon, and compounds that contain carbon are inorganic. Now there's a couple of things that are considered inorganic, and we'll learn about them later in the year, that do contain carbon, but they act like they don't. Okay, so there are exceptions to every rule we're going to find out in chemistry. Okay, so inorganic chemistry, we're going to see things like rock and cement and things like that are inorganic. So an inorganic chemist might develop the materials needed to build buildings like these. So the concrete and steel in those buildings are inorganic. The area that has to do with living organisms is biochemistry. That's all the chemistry that happens inside animals and plants. Okay, you are a chemical factory, and this is what biochemistry deals with. So when your muscle contracts or you digest your food, that's biochemistry. So we might study how the dog is able to catch that frisbee and how energy is basically stored and processed by the dog through the release of energy in chemical reactions. Now, a very important part of chemistry is called analytical chemistry. And this has to do with how chemicals or materials are composed, how matter is composed. So we want to see what makes up different matter. So for instance, if we have sugar, sugar contains carbon, hydrogen, and oxygen. And the amounts of these things will tell us what kind of sugar or starch we have. That would be something an analytical chemist could do. Or for instance, a lot of times we want to find out if there's any metals like lead in our water. An analytical chemist can analyze for that. Okay, another thing that they might look for is carbon dioxide in the atmosphere. So they are oftentimes, even a forensic chemist is basically an analytical chemist. Okay, so what we might be doing if we're an analytical chemist in this picture, we might be looking at contaminants in the water or up in the air. Okay, the next chemist is the physical chemist. It deals with how things react, what's the mechanism, or how fast they react, or how much energy is transferred when matter changes. So physical chemistry is interested in what's the roadmap, basically, of something happening, or how much energy do we have to put into it to make the reaction occur, and what changes occur in structure and form of the matter when it reacts. So a physical chemist might study factors that affect the rate of photosynthesis in trees, because here we have leaves that are starting to fall away, so the rate is going to decrease, so that might be of interest to the physical chemist. As I said, when we're talking about this, the areas intercept and interact with one another, but they're kind of general terms of specificity that each type of chemist will work in, but they use the other forms in all areas. Okay, now we want to look at what a pure chemist would look like. A pure chemist is just simply, or pure chemistry is when we look at things just to know new information, seek new knowledge. Oftentimes a university professor would be interested in finding out new things about how matter reacts or acts in the world. So that would be just for its own sake. They don't expect to have necessarily an immediate practical use. They're just seeking knowledge. Applied chemistry, on the other hand, is doing research with a goal in mind. What are we trying to find? What if we're a pharmaceutical chemist and we want to find a new drug that will treat a specific disease? That would be applied chemistry. Okay, so we basically have a reason to do the work. Now, a lot of times the pure chemist that has found new information is utilized by the chemistry person who is applying it to create a product because that information is there for them to begin their research. Okay, so we have our pufferfish again. Why would you think a biochemist would want to know about a pufferfish or an organic chemist? I'm not going to put this on your questions, but think about that for a second. So a biochemist might want to determine how its toxin acts on the human body, while the organic chemist might want to study the composition of the toxin, because they want to know what the chemical formula is, assuming that it has carbon in it. So what is its chemical formula? And what is its structure? And this is, the biochemist wants to know, how does it work? Okay? All right, here's some questions. I want you to answer this on PlayPosit. Which area of study would you use to determine the components of an unknown liquid? Physical chemistry, biochemistry, organic chemistry, or analytical chemistry? Okay, I'll be back in a second and you can answer that question. Great, I hope you chose D, analytical chemistry. Now, there's some big ideas in chemistry. There's central themes. A lot of times we call chemistry the central science because it's important to biology and it's basically bases a lot of things from physics in it. So it's kind of in the center. So some big ideas is chemistry is essential science. Electrons. Someone asked me the other day, how do I spell chemistry? I spell chemistry E-L-E-C-T-R-O-N-S. It's all about the electrons. The electrons, the electrons, the electrons. Everything is about how electrons move, how they go from one atom to another. It's all about the electrons. Bonding and interactions, reactions, kinetic theory, the mole and quantifying matter, matter and energy, and carbon chemistry. These are the big ideas in chemistry we're going to look at this year. Okay, as I said, chemistry overlaps all the other sciences. Physicists, biologists, astronomers, geologists, environmental scientists, and others use chemistry in their work. Some of you will take environmental science in the future. You'll use chemistry in that course. Electrons and structures of the atoms. Okay, we have elements like carbon, oxygen, and copper are all elements. And elements are composed of particles called atoms. And every atom contains a nucleus and one or more electrons. The type of products obtained in a chemical reaction is largely determined by what happens to the electrons. Okay, most elements, right now we have a periodic table with about 118 elements, but most elements are in compounds. That means that they are collections of two or more elements held together by strong attractive forces. And these forces are called chemical bonds. And we have some bonds which are weak, which are not chemical bonds, but they contribute to the properties of the materials, which we'll see as the course goes on. Reactions are very important because we can make new things. A simple thing as striking a match is an example of a chemical reaction. We have phosphorus on the match, we have oxygen in the air, we make a spark and we get a flame because we need oxygen to have fire. Okay, many times when we make new compounds, energy will be released as light and heat. The compounds in the match head and oxygen are the reactants, and the new compounds are the products. Kinetic theory, I love this word. Kinetic means to move around. And always, 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 even if you are solid, and I will teach you a little dance. See Mr. P's dance, ask him about it. So remember to ask me in class to do my dance for you. Okay, and how fast things move all has to do with what state of matter they're in. The mole is a huge, huge thing in chemistry. The mole, you might think, is a little animal that lives in the ground, but in chemistry, it's a number. And it allows us, it's a very, very big number that allows us as chemists to work with things in the everyday world, even though there's large number of atoms in each small sample that we have. A gram of some substance is many, many atoms or many, many molecules. And the mole helps us do lots of math much more easily. Matter and energy, as I showed you before, equals E equals mc squared. But any process uses energy, and oftentimes it requires heat to start a reaction. We saw that in the chemistry of burgers. Changes in quantity called free energy allow you to predict whether a chemical reaction will actually occur. And we'll talk about that a little bit. It's a little bit more complicated than most of this course. Carbon chemistry, there's 10 million carbon compounds, over 10 million carbon compounds. And you'll find them in plastics, in textiles, in petroleum products, and in all living organisms. So based on what I just talked about, I'd like you to write a little definition of what you think chemistry is the central science. So you could do that and play posit. Some summary notes. I'm not going to read these. I'll leave this here for a second. You can take it down. Stop the tape. Put it in your notebook. Some definitions you should know. Again, stop the tape. Write this down in your notebook. Remember, your notebook is on OneNote. Same here. And that's it. See you in class.